So far, we've been looking at electric fields due to a small number of charges, but that's not often the case. Even if you have a nanocoulomb of charge, that corresponds to having, say, 10 billion charges sitting around. And while in principle you could do it the same way, where you just apply superposition to each and every single one of the 10 billion charges and add up their contributions to the electric field at some point individually, that becomes a bit of a chore. So as an approximation, believe it or not, what physicists will do is say, well, if we're far enough away from something, then it'll just look like the charge is uniformly blurred out somehow, and we don't really have to stress ourselves about where the individual charges are located. A good analogy of this would be, say, if you go to a beach, you might drive up and park somewhere nearby, and as you walk toward the beach, at first all you just see is beach, right? You don't see the individual grains of sand. It won't be until you actually are standing on the beach and looking down at your feet that you will start to see the individual grains of sand. So at that point, in our analogy, you would then have to worry about the individual grains of sand. But if you're far enough away, you can just look and say, yeah, that's beach over there. And we're doing the same trick here. As long as we're not so super duper far away that we can just pretend the whole thing's a point charge, which would be awesome. But not so close where we can see the individual charges. We can just say, yeah, it's just kind of smeared out. And so we'll then be able to use the methods of calculus to get an answer much more quickly than if we were to just add up each charge individually. We'll just be able to integrate. And while technically it's an approximation, when you are talking about having 10 billion or so charges hanging around somewhere, that's a very, very, very good approximation. And so we just roll with it. So to build up a little bit of the machinery we need to do this, we need to talk about how the charge is smeared out over, say, some length. So here, if your charge is distributed out over some length, we call this a linear charge density. Density. And we will say that it is equal to the charge per length. This is a lowercase Greek lambda. Yeah, it's the same one you use for wavelength, but we're running out of letters. So you'd make it like that if you remember the special paper we learned on. And similarly, if, say, it was smeared out over some surface, so let's say, we got some charges, we'll make them negative this time, smeared out over some surface, so again, be charge Q. And now what we'd be worried about is the area of the surface. And we would call this a surface charge density. And we'll say that is eta is defined to be Q over A. So that's a lowercase Greek letter eta. You make it something like that. Now, a lot of books will alternately use the lowercase Greek sigma, which you would draw like that. So the notation isn't 100% consistent in the physics community. I'll go ahead and use eta here. And then finally, if we have some charge distributed uniformly in 3D, we can again do the same trick. So say we got a ball of charge or something, and the charges are distributed all throughout. Well, then what would matter is the charge it holds, Q, and the volume it occupies. And we would say that this is a volume charge density. And pretty much everybody uses rho for that one. And that will be the charge over the volume. So again, that is a lowercase Greek letter rho. You either draw one like that, or some people will do that. Whatever you do, resist the urge to turn it into a tadpole. All right, so the game plan that we're going to do is when we look at a distribution of charge, we're going to find some small differential chunk of it and find the contribution to the electric field that that little differential chunk of charge makes. And then we will integrate over all of the differential chunks. And this is literally adding. The integral sign is actually a old style long S, coming from the Latin summa, meaning to add up. So I think this is probably best explained by working through a few examples. So let's just go ahead and start with a rod of charge. And we would like to find an expression for the electric field strength somewhere along its perpendicular bisector. So definitely remembering our mantra for how to do any physics problem, we know that you can use the acronym STAR, S-T-A-R, for situation, tools, answer, and review. When you're trying to understand the situation, you should always start by drawing a picture. So let's draw a rod of charge. So I'll just note that there's a charge Q here. I'm not going to bother drawing any pluses or minuses because I want to keep the diagram as uncluttered as possible. Oops. Come on. There we go. And I will go ahead and draw in the perpendicular bisector. And let's say that we are some distance D. Our point of interest that we care about right here is some distance D away from the perpendicular, from the rod of charge. And let's also go ahead and say that the length of the rod is L. Now, what we'll do in any of these problems is we go ahead and we will identify a chunk of differential charge dq. And so this is, we'll treat this like it's a point charge, and we'll say it has charge dq. And that may seem a little hanky, but what we're really doing is we're just letting the differential be like a really tiny delta. We can treat it like it's delta q, and we're adding up over a bunch of delta q's. And in fact, there is, in Newton's formulation of calculus, this is exactly where he would go with it. He would say you can treat this as a bunch of basically really tiny deltas and then add them all up. Because Newton had some problems mathematically dotting I's and crossing T's that actually didn't get completely finished up until the end of the 20th century. We tend to go with other formulations of integration, but this is totally legit. You can just think of this as I'm looking at an infinitesimal point charge here. And the thing we can say that the width that it occupies along my rod will be some width dx. Now here's where the linear charge density comes into play. Because the charge is uniformly distributed, not only is it equal to Q over L, but we would have to have the same thing if we took dq and divided by dx. And remember here, I'm treating these as tiny, as basically tiny delta q's and delta x's. If you want, you can go ahead and make a limiting argument to then say that that becomes dq over dx. But it is perfectly fine for our purposes to just say it's a tiny delta q that we're turning into dq, and it's a tiny delta x that we're turning into dx. So the idea here is I'll then just note, because it'll be useful, that dq is q over L times dx. Now, how's that going to help me? Well, the idea here is that I want to find the contribution to the electric field due to this infinitesimal charge, and then I'm going to add them all up. But I'm going to add them all up by integrating, and I need a variable over which I can integrate, and it's not going to work to integrate over q, but will work to integrate over x. So that's why I need to come up with this expression to take me from dq, which I can't integrate over, to dx, which is something I can integrate over. So alrighty, let's go ahead and take a look at what the differential contribution is to the electric field from this. So I'm just following right along. We can mathematically assume that the charge is positive. If it's negative, we just know it'll be inward. And we will say that the contribution to the electric field strength is dE. And this is a vector. Now, the trick that we should realize here is that by symmetry, for every time we've got a chunk of charge over here that's pointing up and to the right, there will be a symmetric one over here that's going to give me a contribution that points up and to the left. And so the horizontal pieces will cancel and we'll only be left with the vertical piece. So we now got the direction up if it's positive, otherwise down if it's negative. So we know that the total electric field at this point is just going to point straight up if we're assuming the rod is positive. Again, if it turns out to be negative, it'll just point inward. So to get my electric field, all I have to worry about is finding the y components to my differential pieces here. So let's just start by saying what the differential contribution of the electric field is. That will be k, or we can write 1 over 4 pi epsilon naught. So then we're going to be taking the charge and dividing by the square of the distance. So my charge is dq. Now this distance here, we can call this r squared. And this distance r, thinking ahead to when we want to integrate, is going to be, let's go ahead and say this is x equals 0. This will be x squared plus d squared, where d again is this distance here. So we take the x, if we put the origin at the middle of the rod, we can take the x coordinate squared, add d squared, take square root. That's the distance there. So squaring a square root just means we drop the square root. So we get that 1 over 4 pi epsilon naught dq over x squared plus d squared. Awesome. Now, keep in mind, this is still a vector quantity, so we found the magnitude that points here. But what we need is this piece of it right there. That piece right there is dEy. So we need to find the y component. Not the end of the world, though, because this angle is the same as that angle. So I go and look at it and say, okay, dEy, let's call that angle, I don't know, theta. Oops, there we go. So let's go and find our dEy. It's going to be my dE that I just found times, well, I want the y component. So this is the adjacent, that's the hypotenuse, so I need the cosine of theta. Now, the cosine of theta is going to be equal to the adjacent over the hypotenuse. So the adjacent is d, and the hypotenuse is that square root. So this will be dE times d over the square root of x squared plus d squared. All right, so if I put it all together, I get that dEy will be, 1 over 4 pi epsilon naught dq over dq, sorry about that, let's just say dq there, times d over x squared plus d squared to the 3/2 power. All right. So now to get my electric field, since I know that the electric field points entirely in the y direction, all I need to do is integrate my dEy. So here, this is where I go ahead and look at this and say, oh, right, I need to integrate over x. So this is where I'm going to substitute in that dq is q over L dx. So let's do that. So I'll be integrating 1 over 4 pi epsilon naught q over L dx times d over x squared plus d squared to the 3/2. And now we have to think from where to where, because this is going to be a definite integral. The length of my rod is L. I put the origin at the middle. So that means that this is x equals negative L over 2. And that means that that is x equals plus L over 2. So my limits of integration will run from minus L over 2 to plus L over 2. All right. So before we evaluate the integral, let's just pull out anything that looks like a constant. That will make our lives a little bit easier. So E will be equal to, well, the 1 over 4 pi epsilon naught is a constant, Q and L are constants, D is a constant, and we'll have the integral minus L over 2 to plus L over 2 dx of 1 over x squared plus d squared to the 3/2 power. Yes, I know. I put the dx right after the integral sign and not at the end of the expression. This is something that physicists do pretty much all the time. This is so that you can keep what you're integrating right next to the limits of integration. This is because sometimes physicists do multiple integrals, and if you're integrating some complicated expression, you don't want to be looking 10 lines down to and then start counting your dx, y, z's, whatever, to figure out what you're integrating over. It's a lot easier if you keep the integrating variable right next to the limits of integration. So That is a difference in notation between how physicists usually write it and how mathematicians do. All right. So anyway, the way that you would evaluate this, because this is a treatment of physics and not a treatment of math, is you would look it up in a table. And when you do, you get that the integral is equal to x over d squared times the square root of x squared plus d squared, evaluated from minus L over 2 to L over 2. So we can cancel 1 power of our d here. That's good. And then if we substitute in the limits and evaluate, we end up being left with that the electric field strength is equal to 1 over 4 pi epsilon naught q over d times the square root of L over 2 squared plus d squared. All right, so that's a cool expression, but how do we know if we're right? Again, you should go through and check your units. So looking over here, 1 over 4 pi epsilon naught, that's just our K. That's Newton meters squared per Coulomb squared. Q is going to have units of coulombs. This D has units of meters. And then we have the square root of meters squared there. Well, the square root of meters squared is a meter. That's a meter. Those cancel the meters squared there. Yay, it's newtons per coulomb, so the units check. Now, the other thing that we should be starting to do is ask ourselves, does this match with the with limiting cases that we know? A limiting case that we can check is if we are far away. Ask yourself, if you're far away from a rod of charge, what will that start to physically look like? Pause and get back with me. All right. Well, if you're far enough away from a rod of charge, it should look like a point charge. So let's test the limiting case, where our d, our distance away from the charge, is much bigger than the length of the charge itself. Well, if that's the case, then our q over d root L over 2 squared plus d squared. If that's the case, that our L is much less than d, then when we square it, L squared is going to be a lot less than d squared. And so then we can go ahead and basically just wish that away. And now you'll have a square root of d squared times a d. And so we get that when we're far enough away, this would be approximately 1 over 4 pi epsilon naught q over d squared, and say, hey, that's a point charge. So it does the right thing when we're far away. We recover the point charge. So that gives us additional confidence that the expression we got was correct. Now, another fun thing that we can do is we can think about the other case, which is, what if we are really close to the charge? So in that case, it's just like, say, if you stand up against a wall. If you go and put your nose right up against a wall, and you look at the wall, would you be able to see the ends of the wall? No, you wouldn't. So similarly, if I'm really close to the charge, but still somehow so close I don't have to worry about individual charges, and that is actually plausible, then my rod will basically look infinitely long. So we do expect that as you go away from the rod, the strength of the electric field should decrease. And also from the symmetry of the situation, we'll get more into how to use symmetry to think about some of these things later. But for right now, you can just say, well, if the rod is basically infinitely long, then if I'm standing right next to a chunk of rod, I can't tell where it is I am along here. And so then the corresponding electric field better look the same everywhere, or else I would have been able to figure out where I was along the rod, and then the rod isn't infinite. So this means that, here, let me scooch my rod over just a bit. There, that looks a little better. So this means that we should expect the electric field lines to always go off perpendicular to the rod, because in a certain sense, if it's an infinitely long rod, you're always in the middle of the rod. And we already found out that the electric field will point away if it's positive or towards if it's negative. So how can we test that? You can't just up and blithely stick in L equals infinity here. If you did, you're going to get infinity squared, and then you're going to take the square root of infinity, get infinity, and then you're going to divide by infinity, and then you're going to get 0. And okay, fine, if you're infinitely far enough away from anything, you get 0, but that's not too good. And yes, I know I treated infinity like a number, and that's not totally legit, but just roll with it here. But the problem is that if the rod gets infinitely long, my charge goes to infinity as well. So this is really going to end up being an infinity over infinity thing. And so we have to be a little more careful. So if I have an infinite rod of charge or a line of charge, actually let's just say line of charge here. There. So let's say we have an infinite line of charge. We can get it by taking our previous result for a rod of charge, which is 1 over 4 pi epsilon naught q over L over 2 squared plus r squared. Take the square root. And we take the limit as L goes to infinity, but we have to keep in mind again that Q is going to go to infinity as well. So we just remember that Q over L equaled lambda. So then that means that Q equals lambda L, and then we'll make that substitution. So then this will be the limit as L goes to infinity of 1 over 4 pi epsilon naught lambda L over the square root of L over 2. Doggone it. There we go. L over 2 squared plus r squared. And this is an infinity over infinity thing. And so you will have to use L'Hopital's rule to obtain the limit. And I will just say that when you do, you get that the electric field due to an infinitely long line of charge is 1 over 4 pi epsilon naught 2 lambda over r. Now in practice, you're never going to have an infinitely long line of charge, but let's say you're got a meter long line of charge. That's totally doable, and you're a centimeter or maybe even a millimeter away from that line of charge. That's as long as you're not like right next to the edge. That actually works out for practical purposes to be infinite enough. And notice here too, the units do check, and you should make sure that they do check. But notice here that now we're falling off as 1 over r. And a way you can think about that a little bit is we saw that for a point charge, the electric field strength wind is 1 over 4 pi, 1 over r squared. And I'll point out that the surface area of a sphere in 3D is 4 pi r squared. Here, in a certain sense, if you think about it, if you could somehow get at the end of our infinitely long line and then look down at it, don't stress yourself too much over that thought, but just imagine you could, then effectively what you'd be looking at is a single dot sitting in a two-dimensional universe. And the equivalent of a sphere in 3D is a circle in 2D, and the equivalent of the surface area would be the perimeter, which is 2 pi r. Don't stress if that didn't make sense, but I was just throwing that in as a little bon mot. Alrighty. In the next video, we will go and take a look at a ring of charge, extending that to a disk, and then eventually to an infinite sheet. Catch you in the next video.